This is the first video in my series on engineering dynamics. But before I jump into anything actually related to dynamics, I want to take a moment to review a few kind of minor but still important topics that are typically covered in earlier courses. In this video, I want to talk about vectors, which are usually covered in previous math courses or in statics, engineering statics. So I want to talk about that for just a little bit. Vectors are important for us to consider because they influence basically everything that we might do when it comes to mathematically evaluating things related to dynamics. And they become important because the quantities that we deal with, like velocity and accelerations, they are vector quantities. And things like forces are also vector quantities. So we want to carefully think about how we handle vectors and what they actually are. So vectors, as I'm sure many of you would recall, are quantities that contain both a direction and a magnitude. And so direction is exactly what it sounds like. It's what direction the velocity is pointing, the acceleration, the force, etc. And the magnitude is how big it is, right? So 1 meter per second versus 10 meters per second would be an example of magnitude. So if I draw a vector, so a graphical representation of a vector is usually done with an arrow, and I might label that. I'm going to label mine R, and oftentimes I'll put this little arrow symbol on top of it to indicate that I'm talking about a vector. Now, to define this vector, we need to know exactly those two bits of information that we've already described, the direction and the magnitude. So usually to do that, we need to specify a coordinate system that we're going to represent that in. For convenience, it might be useful to represent a coordinate system located at the tail of the vector, or with its origin at the tail of the vector. And we'll use a standard XY coordinate system. And then we can specify this director by its magnitude. So basically, how long it is. I'm going to move this label. Magnitude. And then we might specify the direction by measuring the angle off of the x-axis, which is just, would be one standard way to do this. And this would give us an orientation and a length of this vector. Now, of course, the coordinate system is pretty arbitrarily placed. This x and y coordinate system doesn't need to have its origin at the tail of the vector. It could be located in any other position, and then we would need to define the vector based on that new set of coordinates. So this vector, let's pretend it's just any arbitrary number and direction for magnitude. We're not going to give it a specific quantity. This vector could be specified as being 10 units long with an angle of, let's call it 20 degrees, just to make something up. And that's extremely arbitrary, and I've kind of just made those numbers up, but it gives me something to define this vector as. Now, for convenience, it's sometimes useful to know the x and y components of this vector. So if I want to know the x component of the vector, which itself would be represented as a vector, and the y component, which is a separate vector, I could define these things using my standard trigonometry. So I've got an angle, and this angle gives us a right triangle, where the right angle is over here in the bottom right-hand side. And then I can use my trigonometry functions like sine and cosine and tangent to define what the x and y components of this would be. So hopefully everyone is familiar with standard conventions for these things, but basically my vector in the x direction would have that magnitude of 10 brought down, and because I'm talking about the x component, which is the adjacent side to my angle, I would be using the cosine of my angle. And for the y component, I would do exactly the same thing, but now I'm using the y component. So that allows me to specify that vector in its x and y components, and I would know what the component or what the magnitude of those two vectors would be, rx and ry. Now I could similarly define a second vector, and a second vector I might define, let's just call it s. So suppose I take s, and I'm going to redraw my r vector here. Suppose I take s and I add s on to the end of r, like this. So now I have these two vectors, and I want to figure out what the resultant of these two vectors is. So if I add two vectors, I get the result, and the resultant is going to be the vector that goes from the tail of r all the way to the head of s. So let's call this resultant A. I'm arbitrarily, again, picking that to represent addition. And I would say that A is equal to the vector addition of R plus S. So I have these two vectors being added together. Now, one way that I can deal with this is I can take the vector addition in the x and y components, which you may have seen before, basically saying that, let's get a different, go back to my basic color here. Basically saying that AX is going to be equal to RX plus SX, and AY is going to be equal to RY plus SY. Realizing that any of these quantities could be positive or negative, depending on whether they go up or down, and so forth, as my sign convention of my coordinate system. Another thing that I might want to know, or another way to analyze this, is to treat this as a triangle, which it is, right? And use something called the triangle rule, or triangle rules, and one of them being the law of sines. And the law of sines is useful because it gives us more information about these three vectors that I maybe don't have from the start. And the law of sines, written mathematically, is A over sine A, B over sine B. Note that I'm using lowercase letters and capital letters over sine C to represent different things. Now these letters don't necessarily correspond to the vectors I've shown up here, but instead, if I have, again, an arbitrary triangle, these letters are used to denote the side lengths, A, B, and C, and the corresponding angles to those sides. So the lowercase letter A, B, C are the length, the magnitude of those sides, or the magnitude of my vectors, if I'm talking about a vector triangle up here. And the uppercase letters are the angles corresponding with those vectors within their triangle. So this can be useful in that I can calculate an unknown if I know at least three of these quantities. I can start calculating the other unknown values, whether that's magnitude or angle. We should also be familiar with the law of cosines, which is another similar function that can be useful. And the law of cosines says that let's write this a little smaller to indicate that it's lowercase, c squared equals a squared plus b squared minus 2ab cosine c. So this might look, or at least the first portion of this might look somewhat familiar to you, this first portion, as Pythagoras' theorem, which is true for right-angled triangles. However, this is a little bit more general version of that in that the angle C doesn't necessarily have to be 90 degrees, and therefore we get this function. If C was 90 degrees and we were talking about a right triangle, the cosine of 90 is 0, and therefore this last term would drop out of the equation. We'd have Pythagoras theorem. So the stuff that I've talked about here is just some basics of working with vectors, a little bit of geometry, and some things that we would find useful for us as we go through with velocity vectors and acceleration vectors and the things that we want to talk about in a dynamics course. Thanks.